compounds with an asymmetric center, having 4 different groups, and asymmetric center can be used interchangeably with the term chiral center. Some people say that a chiral center rather than an asymmetric center. You should be prepared to hear this called many different things. So, my method. We identify the carbon that has 4 different groups. If you're in a condensed form, this is usually counting. So I have on one side 3 carbons, on the other side 4 carbons. It's also bonded to a hydrogen and a hydroxyl group. That is 4 different groups. If you're looking at the skeletal structure, you could also count. My method is just to say or write the group. So at the asymmetric center for 4-octanol, I have a propyl, a butyl, a hydrogen, and an OH group. That's 4 different things. It is an asymmetric center. If you look at the central carbon, we have on one side 1 carbon, on the other side 2 carbons, a bromine, and a hydrogen bonded to the carbon that has a branch. So it's bonded to methyl, ethyl, bromo, and hydrogen. That's 4 different things. The molecule on the far right, we have 2 centers that I will look at. I will look at both branches. If you look at the branch that they did not assign a star to, this carbon is bonded to a methyl group, a butyl group with a methyl branching off of it, another methyl group, and a hydrogen. Wait, did I say another methyl group? 2 methyl groups, then it doesn't have 4 different groups. So this carbon is not an asymmetric center. Now we can go on to the next branch point and identify if the groups are the same. I have a sec-butyl group, or a 4-carbon group with a methyl branch. 3-carbon group with a methyl branch. 1, 2, 3, methyl branch. I have a methyl group, and I have an ethyl group, and I have a hydrogen. That is 4 different groups. That is an asymmetric center. Molecules that have asymmetric centers have non-superimposable mirror images. The 2 molecules generated by drawing the mirror image of 1. Okay, so if we have 2-bromobutane, for example, and we build it, and then we draw its mirror image, we have actually 2 distinct molecules. They are not superimposable, so there are 2 molecules. The relationship of these 2 molecules as non-superimposable mirror images uses a special term to identify what they are. We call these stereoisomers enantiomers. Enantiomers are different compounds, but they can be separated. They have, for the most part, the same chemical and physical properties. The only difference is the direction in which they rotate plane polarized light. But the boiling point, the melting point, and other physical properties and the solubility are identical between stereoisomers. One major difference is that one stereoisomer does not fit into another for an enzyme. Okay, so we have an enzyme that fits a molecule with a triangle, a square, and a circle. Okay? So this molecule has a mirror image. So let's draw our molecule. We have triangle, square, and circle. And this is going to fit into my enzyme. Okay? If I draw the mirror image of this molecule, then what I have is a circle followed by a square followed by a triangle. And then if I try to take the mirror image molecule and put it into the enzyme, it will not fit because the circle would overlap with the space intended for the triangle. And that is the biological significance of enantiomers. Enzymes are specific to only one molecule of a pair of enantiomers. And so it's essential that in the drug industry, both enantiomers are characterized and tested because one will go, if both are produced in the medicine, you have to purify it so that only the desired enantiomer that will interact is present. And this is called, I hope you learned in biology, the lock and key mechanism of enzymes. If I want to write on the bottom, I'll write on the bottom. Irritating. Lock and key. I apologize. Lock and key. Okay. Moving forward. Ooh, an activity for you. Okay. So we're not going to call it a quiz. Let's call it a practice quiz. Look at slide 22. I'll put in a little submit assignment for slide 22, and you guys can answer the questions. Let's say it'll be due by Sunday, and what I want you to do is to determine the highest priority groups, comparing, I've labeled each group as A, B, C, and E. It should be A, B, C, and D, not E. D. And then comparing AB to CD and AC. I mean, the question is, how do you determine the highest priority groups? Am I going to compare A and B and C and D? So do I compare A to B and C to D? Or do I compare A to C and B to D? Which is the correct method? Comparing groups on different carbons or comparing the groups on the same carbon? Then you tell me what determines priority. Next, what are the two highest priority groups of the molecule? And then, is the double bond E or Z? Okay, enantiomers. Non-superimposable mirror images. So they are chiral, which means they must have an asymmetric center, because we already saw that the definition of chiral is to have non-superimposable mirror images. And we also said that a molecule that is chiral has an asymmetric center. So enantiomers are chiral and they have an asymmetric center. Chiral and achiral molecules. Okay, a chiral molecule has a non-superimposable mirror image. If you build the three-dimensional structure and you build its mirror image, they will not be superimposable. The term achiral refers to a molecule that does have a superimposable mirror image. This would mean that there is no asymmetric center. In this case, the molecule and its mirror image are superimposable. An asymmetric center versus a stereocenter. What is a stereocenter? A stereocenter is an atom at which the interchange of two groups produces a stereoisomer. Now, this is true for both easy cis-trans and asymmetric centers. So the cis and trans carbons are stereocenters, and so is the asymmetric center carbon. The distinction is that an asymmetric carbon is always defined as an atom attached to four different groups. And what that tells you is that an asymmetric carbon, because it's attached to four different groups, bonded to four different groups, it has four bond sites and it has four electron domains. And so an asymmetric center will always be an sp3 carbon. Whereas stereocenter could be either an sp2 or an sp3 carbon. Not all sp3 and sp2 carbons are asymmetric or stereocenters, but that is one characteristic that it must have to be a asymmetric center. So, example, a methyl group at the end of this molecule is an sp3 carbon, but it is not attached to four different groups, so it is not an asymmetric center. A stereocenter could be either an sp3 or an sp2 carbon, but only sp3 carbons that are asymmetric centers are stereocenters, and only sp2 carbons that are part of a cis-trans or EZ double bond are stereocenters. Okay. How to draw enantiomers. Perspective formulas of the enantiomers for 2-bromobutane. You should be familiar with, make yourself familiar with drawing perspective formulas. The solid bond coming out towards you, the dashed bond going back away from you, the bromine and the hydrogen being perfectly flat in front of you. So they should be parallel to you when you're looking at them. Then these two, the methyl and the ethyl, when you build the three-dimensional molecule, are making a V with the methyl going back and the ethyl coming forward. Okay, so that is the perspective formula. Fisher projections are the method of displaying molecules preferred in biochemistry. It draws it flat and it shows the asymmetric center as the center of the Fisher projection. Fisher projections have the following bond types, which must be memorized. All horizontal bonds are coming out towards you, and all dash bonds are going back away from you. If you build the three-dimensional molecule, rotate it around until you have bromine and hydrogen on a V that is along the x-axis, but with the V pointing at you. Then the methyl and the ethyl of the molecule that you build will be on a V that is in line with the vertical axis, but pointing away from you. It's much easier to draw the mirror image of a Fisher projection because it's simply drawing a cross and filling in the groups. Naming enantiomers. So we know that enantiomers is a pair of two unique isomers that are non-superimposable mirror images. So we have to have a way of distinguishing them by name because they are not the same thing. In order to name, the way that we differentiate enantiomers by name is to determine their direction in which we go from highest priority to lowest priority group. So when we name these molecules, one will be S and the other will be R. The group that is determined to be S priority, or S, will have the highest priority group moving counterclockwise as it goes toward the lowest priority group. And the molecule that we label as R will have the highest priority group, and then we move around the molecule in a clockwise direction until we get to the lowest priority group. So we must number the groups by priority, and the priority again is by atomic number. They've labeled our molecule for us. Bromine is the highest priority, then ethyl, then methyl, then hydrogen. And if you move from 1 to 2 and 2 to 3, that is moving in a counterclockwise direction. Thus, the molecule on the left is called S2-bromobutane. The molecule on the right has the priority groups moving as follows. 1 to 2 is like going from 12 o'clock to 3 o'clock. And then we go from 3 o'clock to 6 o'clock, and etc. That is the clockwise direction. So this molecule on the right is R2-bromobutane. And that is how we distinguish one enantiomer from the other. Naming of enantiomers. Draw an arrow from 1 to 2 to 3. Leave 4 off. Do not draw an arrow to 4. The rule is that we can pass 4 on the way to 2, but we cannot pass 4. So as we move from 1 to 2, we can pass carbon 4. I think, maybe, no. Just ignore that. I apologize. So completely ignore carbon 4 when you're drawing your arrows. Draw an arrow from 1 to 2 and 2 to 3, and then ignore carbon 4. Okay? Or priority 4. So 4 could be, the lowest priority group could be hydrogen, or it could be any other atom, as long as it has a lower atomic number than the previous group. Please don't automatically assume that the lowest priority group will be hydrogen. All right, if the lowest priority group is on a hatched wedge, then R is clockwise and S is counterclockwise. So this moving from 1 to 2 to 3 and determining clockwise and counterclockwise is only valid when hydrogen is on a hatched wedge. That is the convention. If you have a prospective formula, your lowest priority group must be on the hatched wedge. Not just hydrogen, but whatever the lowest priority group is. Okay. What do you do if the lowest priority group is not on a hatched wedge? Your book has a method that it suggests. The book suggests that you interchange the lowest priority group with the group that is on the hatched wedge. So we're going to interchange the group 3 labeled methyl and the group 4 labeled hydrogen. Then we determine the configuration. But because we switched two groups, the configuration of the molecule that we determine is opposite of the original molecule. And that will be shown on the next page. I will show you a different method of determining this other than exchanging group 3 for group 4. And that is to picture the molecule in three-dimensional space and rotate about the bond from carbon to ethyl. So if you think about holding the three-dimensional molecule with the ethyl and the hydroxide being completely flat in front of you, and the methyl pointing back and the hydrogen pointing forward. And then you hold the ethyl carbon and you twist the molecule so that it moves, so that the methyl moves to the back, okay? So you're gonna twist the molecule counterclockwise, basically, so the methyl is moving back, but you're not gonna stop with the methyl in the back. You're gonna stop when the methyl reaches the same position as the hydroxide group. So when you twist the molecule so that the methyl twists all the way around to the hydroxide, so now the methyl is the one that is horizontal in front of you, what happens is that the hydroxide then moves to the position of the wedge pointing towards you, and the hydrogen moves to the wedge pointing backwards, the hatched wedge. And so by rotating the molecule, so take this three-dimensional structure and rotate it about the bond. If we draw the result of the rotation that I described, what we get is that ethyl stays where it was. As I said, I rotated it until methyl came all the way into the position of hydroxide, hydroxide came into the position of hydrogen, and hydrogen went into the position of the methyl group. So now my line bond is to methyl. I guess I could draw it somewhere else. Okay. Let's draw it over here. Ethyl stays where it was. My line bond is now to methyl. My solid wedge is now to hydroxyl. And my hatched wedge is now to hydrogen. The hydrogen is on the hatched wedge, so now I can follow regular rules in determining highest priority to lowest priority. The highest priority group is the hydroxyl group, so we'll call that 1. Next is the ethyl group, and last is the methyl group. We can completely ignore hydrogen as we determine we completely ignore the lowest priority group as we draw our arrows from 1 to 2 to 3. So if we draw an arrow from 1 to 2, and then from 2 to 3, the direction that the arrows is going is counterclockwise, or S. All right, so that would be one method of determining rather than switching group 3 and group 4. Now here's what I was trying to say about the method of switching group 3 and group 4. Notice that if I switch group 3 and group 4, the direction of the arrows is clockwise. So when I exchange group 3 and group 4, I am creating the enantiomer. So this is the enantiomer R, but because it resulted from the exchange of two groups, I can say that the original was S. Whichever of these two methods works the best for you is the method that I recommend. And here's just an example of what the molecule looks like drawn in bigger scale when we exchange the groups. So if I'm doing a group exchange rather than a rotation, what I do is that I do not actually redraw the molecule. Instead, I write what I am interchanging in another color ink next to it, and then I label the priority groups using the colored atoms and determine the direction, whether it's R or S. But because I have those red atoms there, it reminds me that what I find, R or S, has to be switched to the opposite when I name the original molecule.